Can folks in the chat hear me okay? Wonderful, thanks. Okay, so as always, don't forget the seating survey. This week, the due items are going to be the Newton homework on Friday. I haven't announced this publicly yet, but I am going to move the due date for the small group activity to Thursday with the quiz due on Friday, and in accordance with the preferences expressed on Piazza. So I will get that implemented this afternoon. This is the last week of material for the third exam, and that exam is going to be released next week. So next week will be review. Once again, I was not able to get the content videos together for this week, so today and tomorrow will be identical classes where I am going over the new material for this week. And then Wednesday and Thursday will be days to address questions that anybody has. Does anybody have any logistical questions before I get moving on the content for today? Okay, so the first topic that we want to look at is the last main acid-base topic for the semester, titrations. And so the general idea of a titration is that we are performing an acid-base reaction in a controlled way to monitor the change in pH as we are adding acid to base or base to acid. So the typical setup to do this kind of experiment is to have a burette. This is called a burette that has the substance that we are adding in it. This is a zoom in of it, and we have a stopcock on the bottom, which we can turn in order to release controlled amounts of the liquid. The burette has graduations along it that are extremely precise. So if we take our starting volume and then our final volume and subtract the two, that tells us at any given point how much we have added. This is suspended over our reaction vessel, in this case a beaker. We add it a little bit at a time, and we monitor, in this case, the pH as the reaction proceeds. So when we do this, we can generate a plot of pH versus the amount of solution that we have added to generate what is known as a titration curve. So that's kind of the overview of what we're doing. Let's take a look at some examples of what will happen over the course of a titration. So the first example we'll look at is the simplest one, which is going to be a strong acid, strong base titration. So we are going to start with the beaker having 25 milliliters of 0.100 molar HCl. And we are going to add to it different amounts of 0.100 molar sodium hydroxide. And so we are going to start in this analysis to look at how we would calculate what our pH would be at several different points along the titration. I'm going to start with no added sodium hydroxide. We will then look at adding half as much sodium hydroxide as the hydrochloric acid we started with. We're going to look at adding exactly the amount that we had of the HCl, and then half again as much. So those are the 4 places we're going to look. So for the first one, for A, where we have added no sodium hydroxide, finding the pH is very straightforward because all we have is 0.1 molar HCl. So 0.100 molar HCl, which translates into, because this is a strong acid, it fully dissociates, it's 0.1 molar in hydronium. And, well, molar in hydronium. So remembering that our pH is negative log base 10 of our hydronium ion concentration, then this is very simple. This is a pH of 1. Because 0.1 molar is 1 times 10 to the minus 10th, excuse me, 10 to the minus 1. And so our pH is 1 in this case. Let's look at our second case now, where we've added a half equivalent of the sodium hydroxide. So to do this calculation, we need to figure out the number of moles of hydronium we have, which is going, that we're starting with, which is going to be our 25 milliliters times our concentration, 0.100 moles H3O plus over 1 liter H3O plus. And then we have to convert milliliters to liters so that our volumes cancel correctly. Milliliters, milliliters, liters, liters. And we find that we have 2.5 times 10, let's see, first, 0th, 10 to the minus 3 moles of H3O plus. Now, how much hydroxide did we add? Well, we added 12.5 milliliters. We have the same concentration. And we find that we have 1.25 times 10 to the minus 3rd moles of hydroxide. Now, because both of these are strong acids, they neutralize each other until you run out of the hydroxide. So that means that after the neutralization reaction, we have our final is going to be the amount we started with, 2.5 times 10 to the minus 3, minus the amount of hydroxide that we added, because that much of the hydronium is going to react away. And we find that we have left 1.25 times 10 to the minus 3 moles of hydroxide, excuse me, hydronium left. Now, what volume is that in? Because we need a concentration. Well, we have, so we take 1.25 times 10 to the minus 3 moles of the hydronium over our volume, which is going to be 25 milliliters from the initial volume, plus 12.5 milliliters from the amount that was added for 37.5 milliliters. And to make this molarity, we have to convert milliliters to liters. And we find that our concentration of hydronium in the final solution is 1.25 times 10 to the -3 times 1,000 divided by 37.5 gives us 0.0333 molar. And so our pH is going to be minus 1.48. Okay. So do we have any questions up to this point on this? Okay. Let's look at our case number, letter C, where we've added an equal amount of the sodium hydroxide as the hydrochloric acid. So this is equal both in terms of the volumes, but because the concentrations are also the same, that means we've added the same number of moles of hydroxide and hydronium. So that means we now have completely neutral water. And so we can just write down straight off the bat that our pH is going to be 7 for C. How did the pH go down when adding a base? The pH, oh, sorry, that is not negative 1.48. That should be positive 1.48. I apologize. So yes, the pH should have gone up, and it did. Now question D, part D, where we've added 37.5. So what we do here is we assume that we're starting with the neutral at C, and we're adding 12.5 milliliters more of the base. So that means that we now have 12.5 milliliters of our hydroxide solution, which is 0.100 moles of hydroxide for every 1 liter of hydroxide. And convert 1 liter, 1,000 mils. We find that we have added 0.5 times 0.1 divided by 1,000. I did something wrong there. 12.5 times 0.1 divided by 12.5 times 0.1. Why is my calculator not, what am I doing wrong? 12.5 times 0.1 divided by 1,000. That's better. 1.25 times 10 to the -3 moles of hydroxide. Our volume at this point is 25 mils plus 37.5 mils. So we have 62.5 mils. So 1.25 times 10 to the -3 moles over 62.5 milliliters, 1,000 milliliters over 1 liter. And we find our concentration divided by 62.5 times 1,000. Did I do that right? 0.02. And that is our concentration of hydroxide. I want to double check that. 1.25 times 10 to the -3 divided by 62.5 times 1,000. Nope, I did that right. And so our POH at this point is 1.70, which means that our pH is 14 minus that, or 12.30. So this takes you through how to calculate the pH in the various different regimes that we are dealing with. At the very beginning, before what we call the equivalence point, at the equivalence point, and after the equivalence point. Now, we could have picked any values in between. So I put together a spreadsheet to do that, and this is the titration curve that you end up with. And so what you should notice here is that the pH is not changing very much until you get really close to the equivalence point. This point here at 25 milliliters is known as the equivalence point. And that happens when you have an equal amount of the acid and the base. And in this case, we end up with the pH of 7. And you notice that is happening at 25 milliliters. The detail that you should really notice very carefully here is just how steep this curve is at that equivalence point, which means that you go from very low pH to very high pH extremely quickly. And so putting in just a drop at a time once you get close here, you can, if you can determine which drop it is that you've added that produces the equivalence point and the very rapid change, then you have extremely precisely determined that, that volume for the equivalence point. And we're going to use that in a little bit. Now, I said that this was the simplest example of a titration curve because it is a strong acid and a strong base. Let's now do the same thing where we have a weak acid. So we'll, instead of using HCl here, we're going to use acetic acid, CH3COOH. And we're going to look at exactly the same points here. So we are now looking at a weak acid with a strong base that we are adding to it. So what is this going to look like? Well, the first thing we need to know is our Ka of the acetic acid. So the pKa of acetic acid is 4.76, which means that our Ka is equal to 10 to the minus 4.76 molar, which equals 4.76, change sign, 10 to the x. It's going to be 1.74 times 10 to the negative, whoop, what did I just do? I hit a button. 4.76, change sign, oh, no. That's what I meant to do. 1, 2, 3, 4, 5. Yep, 10 minus 5. Okay. So let's start with A, where we've added none of the sodium hydroxide yet. At that point, we have simply 0.100 molar acetic acid. I'm going to abbreviate it HA. So you can do this using an ice table. So HA plus H2O is in equilibrium with A minus plus H3O plus. Zero 0.10000 minus X, 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 0.100 minus x, x, x. Let's assume that x is small compared to 0.1 and see if that ends up working for us. So we now have 1.74 times 10 to the negative fifth molar equals x squared over 0.100 molar. So we get 1.74 times 10 to the negative sixth molar equals x squared. And so x, sorry, that should be molar squared. Nope, that one's not, this one is. And so x equals the square root of that number, 1.74, can't type, 1.74 times 10 to the negative sixth square root. We get 1.32 times 10 to the minus 3, which is certainly small compared to 0.1. And so our pH is going to be the negative log 10, base 10 of this, or 2.88. Okay. So that is our initial concentration that we're working with. Our second data point that we're going to look at, B, is going to be where we have added half as much sodium hydroxide as acetic acid that we had. Now, if we look at this reaction right here, and we add to it half as much sodium hydroxide as the acetic acid, then that's the same thing as having equal amounts of HA and A minus, because the hydroxide is pulling off the proton from half of these. So we are going to be in the buffer region when we do this. So the way to look at this is to say that we have we need to figure out our concentrations. Well, we need to figure out our number of moles to begin with. So since our volumes are changing. So 25 milliliters of our HA times our initial concentration of 0.100 moles of HA over 1 liter of HA. 1 liter is 1,000 milliliters. And we find that we have, once again, the same number we had before of 2.5 times 10 to the negative 3 moles of HA that we started with. Now we are converting half of that to A minus because of the hydroxide. And so we end up with our concentration of HA that we are going to start with is going to be 1.25 times 10 to the minus 3 moles of HA over our volume, which is going to be 25 plus 12.5 or 37.5 milliliters, 1,000 milliliters and 1 liter, to give us 1.25 times 10 to the negative 3 divided by 37.5 times 1,000, going to give us 0.0333 molar in HA, and our A minus concentration is going to be the same thing. And now, because we know we're in the buffer region, we can use the Henderson-Hasselbalch equation to determine the pH. It equals the pKa plus the log base 10 of A minus over HA. Well, these are the same. So log base 10 of 1 is 0, so our pH just equals the pKa, which equals, we wrote it down before, 4.76. So that is how we determine the concentration, determine the pH before we reach the equivalence point. Okay, there's a question from the chat. Would you know X is negligible compared to 0.1 before that calculation? Generally, the easiest thing to do is to go ahead and assume that it's small and then you check it, because the math is so much easier when you do that. If you don't assume it, then you have to go through the quadratic formula. There's nothing wrong with not assuming it if you don't mind doing that, but it doesn't necessarily matter. Second question, how do you know that half of HA will be reacted with? So the idea is that if you react a strong base with a weak acid, and you have put in half as much of the base as you have of the acid, each base molecule, the OH, is going to pull off the one proton. And so that means that half of the acetic acid will have reacted away at this point because we have added half as much. So what that does is that if we decided to do this in an ice table, what it would do is give us equal amounts right here. We then plug in the X in order to see if it's small, and it ends up being because we are in the buffer region. Okay, so this is how, while you're in the buffer region, then you can calculate your pH using the Henderson-Hasselbalch equation, like this. At the equivalence point, which is our third point right here, then we have to recognize that if we imagine the same thing happening we did before, then we'll have converted all of the acid into its conjugate base, the A minus. And so the active reaction at that point is going to be A minus plus H2O is in equilibrium with HA plus OH minus. So the standard base reaction for a weak acid. For a weak base, for the conjugate base of the weak acid we were starting with. And so here, we have converted all of our acid into the conjugate base. We previously determined how many moles of that acid we had. The volume that this is in is now 50 milliliters. So our concentration here is going to be, there's a sheet of paper here for that. So we have 2.50 times 10 to the minus 3 moles of A minus in 50 milliliters, and we convert mils to liters. And we find our initial concentration of A minus going to be 2.5 times 10 to the negative 3 divided by 50 times 1,000 gives us 0.05, oops, I'm off the bottom screen, aren't I? 0.05 molar A minus. And if we'd stop to think about it, that's how much acid we started with in twice the volume. So it makes sense that we would end up with half the initial concentration. So 0.05, 0 minus x plus x plus x, x, 0.05 minus x. Our Kb equals x squared over, let's assume x is small compared to 0.05, 0.05. Now, how do we find Kb? Well, remember that Ka times Kb equals Kw for an acid and its conjugate pair. So this is going to equal 10 to the negative 14th molar squared over our Ka, which was 1.74 times 10 to the minus 5 molar. So our Kb is, I'm sorry, so our Kb is going to be 1e14 change sign divided by 1.74 times 10 to the negative 5th, and we get 5.75 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molar. So we multiply through by 0.05. X squared equals that times 0.05. 2.87 times 10 to the negative 10th molar. Excuse me, so there's a molar there. So molar squared. And so X is going to be our square root of that, or 5.36 times 10 to the negative 1, 2, 3, 4, 5, 6 molar, which is our OH minus concentration, which means our POH equals 5.27. And so our pH is going to be 14 minus that, or 8.73. Okay. So that's how you determine it at the equivalence point, determine the pH at the equivalence point. How about once you pass the equivalence point? Well, once you pass the equivalence point, then you're essentially just dealing with the amount of base in excess of the equivalence point that has been added. So we know how much base gets added going from 25 mils to 37.5 mils. We calculated that earlier as 1.25 times 10 to the minus 3 moles of OH minus. And we already dealt with the same concentration of, the concentration being in this volume before. So we get a concentration of OH, just like we did before, of 0.02 molar, which then gives us a the same POH we had before, which I already calculated. Oh, where did I calculate that? Oh, right up here was this. So we have a POH of 1.70. Therefore, our pH is going to be 12.30, just like it was in the strong acid, strong base case. So none of what we went through here is really new material, but what you have to keep track of as you're doing these calculations is which regime in the titration you're in. If you are in the region before the equivalence point, at the equivalence point, or past the equivalence point. The approaches you use can be different because there may or may not be an equilibrium that is playing a role at that point. Now, when I showed you a minute ago what the titration curve looks like for the strong acid, strong base case. And just as a reminder, it looked like this right here, where the equivalence point was at pH of 7, and the volume added was equal to the volume of the original acid that we started with. It is only going to be equal volumes if the concentrations are the same. When we look at the weak acid strong base case, this is what it looks like. The equivalence point happens at the same volume as it did in the strong acid strong base case. But the pH of it is different. Notice that our pH at the equivalence point is higher. It's the midpoint of this plot right here. And notice as well this region around here, where the pH is not changing very much. This is the buffer region. And at 12.5 milliliters, this is known as the half equivalence point. That is the point at which the concentration of HA equals the concentration of A minus. And here you'll notice that when we're at the half equivalence point, the pH is actually pretty precisely determined. So if we find the equivalence point, we half the volume to find the half equivalence point, and then we very precisely determine the pH at that point. Due to the Henderson-Hasselbalch equation, that pH is the pKa. So this titration curve approach is a very, very precise way to determine an equilibrium constant for a weak acid. Okay, some questions here. Will we have a graph to tell that, or how do we know that, where that is where we are in the titration curve and this which process to use? So in the general case, you would have to generate the full curve in order to know exactly where you're going to be. If you already know both concentrations, then you know where the equivalence point is simply by comparing the concentrations. If you don't know the concentrations, then you would have to generate the curve, and the curve will help you determine the concentrations because of when you find the equivalence point. The equivalence point is going to be the point where the amount of base added, the moles of the base added, is equal to the moles of the acid you started with. And so if you don't know the concentration to begin with, you run this experiment, find the equivalence point, and then that equivalence point tells you the number of moles that you had, and so you can just divide by the volume you started with, and that's your concentration. So this is one of the most precise ways to determine the concentration of an acid or of a base if you make a standard solution of the opposite. So you would make a precise concentration of your sodium hydroxide, you might not, and you don't know the concentration of your unknown acid, finding the equivalence point gets you the concentration of the acid. Okay, there's a question here. For example, on the exam. Well, I mean, we could do this in a number of different ways. I could give you a titration curve and identify where particular points are, and from those points, you then determine you would then determine what the concentration is. You could determine what the pKa of the acid is, and then maybe by comparing to a list of different pKa's, you could identify which acid you're dealing with, something like that. I mean, there are all kinds of different ways that you could use this information. Alternately, if you are, just like we did in our first set of calculations, if I tell you what the concentrations are and then ask you what the pH will be at a particular addition volume, then simply by comparing the number of moles that you've added, you know where you are relative to the equivalence point. So if you've added less than the amount of acid that you start, if you add less base than the amount of acid that you started with, you're before the equivalence point. If you've added more, you're above the equivalence point. Okay. So very, very often, people will set up this experiment and they don't want to have to trace out the entire curve using a pH meter and writing down all of the numbers that are associated with it. What people will often do is use a chemical called an indicator. An indicator is a substance that acts as a Bronsted-Lowry acid or base that has one color when it is protonated and a different color when it is unprotonated. A very common one is something known as phenolphthalein. I'm butchering the spelling of this. That's clearly not how it's spelled, but phenolphthalein, which at low pH is transparent, it's clear. At high pH, it is pink or violet, depending on how much you put in. And so as you are going along a titration curve, it's clear, it's clear, it's clear, it's clear, it's clear. And then you start to notice that a drop that hits, because you have a stir bar that's going down here, a drop that hits becomes pink, and then as it disperses, it will then go clear again. At that point, you slow down how quickly you're adding your base. And when you start adding it drop by drop, it'll be pink and then fade away, pink and then fade away, until it goes pink and then it stays pink for the whole, and the entire solution becomes pink. That last drop that you added means that you have crossed the pH threshold of that particular indicator. And so if you pick an indicator where that transition between colors is in some region around your equivalence point, because the titration curve is so steep right there, that means that to the nearest drop, without even using a pH meter, you have determined very precisely where the equivalence point is. So in the online textbook, there is this figure that shows a variety of different indicators which transition from one color to another color over different pH ranges. And you see there are indicators that have ranges where they change color all the way from pHs of 1 up to about pHs of 11 or 12 in this case. And so here, for example, is the phenolphthalein that I was mentioning. Oh, my spelling wasn't as bad as I thought it was. Yeah, okay. It's still wasn't perfect, but yeah. So you see here that it's transitioning at in the range of pH 8 to 10, mostly around 9-ish. And if we look back here, our pH change for our strong acid, that would work, but our titration for our weak acid, that's really in the right range very, very nicely. And so what you can do is if you, this is showing here strong acid titration, weak acid titration. We have the equivalence point in different regions here. And so different indicators will have different ranges where they change pH, so change color. So you could see here that the litmus pH range here would work very well for the strong acid, strong base situation, but it would not work well for the weak acid strong base case because it would start changing down here in the buffer region. Okay. So those are the basics of titrations. First, let's just talk about the concepts. Does anything about the concept of the titration not make sense that I could help try to clarify? What it is we're trying to do with it, how we set up the experiment, that sort of thing. Okay. Any questions on the calculations and how we do the calculations to determine pH in different regions? Okay. And anything on indicators. All right. Next thing I want to show you is the titration of a polyprotic acid. So this here shows the titration of phosphoric acid, which happens to be one of the acid components that is being examined relatively closely in the group activity for this week. And so it is a triprotic acid. I'm sure this may be a little hard to read. So we're looking at H3PO4, which loses its first proton to become H2PO4 minus, loses a second one to become HPO4 2 minus, and then can lose its third one to become PO4 3 minus. And what you notice here is that there's the first equivalence point, which is the point at which you have added enough base to fully deprotonate it once. There is a second equivalence point where you've added enough base to fully deprotonate it twice, and a third equivalence point where you have added enough base to fully deprotonate it 3 times. Now, once you get to this region up here where the pH is approaching 14, you'll notice that we're not getting a similar line going up as we do on the other two. That's because simply we're running up against the highest pH that you can really get in water in these cases. But if you determine that this is the first equivalence point, this is the second equivalence point, this distance should be equal to this distance, and they should also be equal to this distance, so you can identify where the third equivalence point is that way, even without seeing the curve go up. Each of these also have the half equivalence point where you've added half the volume to get to that equivalence point. And that tells you directly the pKa of each of the various acid steps. So the pH at the half equivalence points gives you that pKa directly from the plot. So general procedure here that you would do, and you may in fact, I don't know if you've done this yet in the chemistry lab or not, but at some point in the lab, I believe you do a titration of phosphoric acid. And what you're doing is you're measuring the position of the equivalence points. You are taking half that distance back to find the pKa of each of the deprotonation steps. That is it on acids and bases for now. Any clarifying questions before we get into our last equilibria content for this week? Okay, so the remaining topics are on equilibria are simply dealing with some special cases. There's really no new content in this. It's just a bunch of new examples. The first of them is going into something that we've already mentioned a little bit, the KSP, the solubility product of a substance. Solubility product, which is for any ionic compound, it is simply the equilibrium of the compound in its solid form with its ions in its dissociated form in solution. And so this is called a solubility product because the thing on the left doesn't enter into the equilibrium expression. So the entire solubility product is just the product of the concentrations of the ions. So if you take any particular ionic compound you can think of, let's say aluminum sulfate. Okay, so Al2SO43 in equilibrium with 2Al3 plus 3SO42 minus. And so your KSP for this is concentration of aluminum 3 plus squared, concentration of SO42 minus cubed. So the solubility products have a lot of extremely important types of impacts on everyday life. So let's look at an example of that. So this here is a set of coupled equilibria that are all happening simultaneously in water. So carbon dioxide in the gas phase is in equilibrium with dissolved carbon dioxide. Carbon dioxide in the aqueous phase is in equilibrium with carbonic acid. Carbonic acid can lose one proton to make bicarbonate. Bicarbonate can lose a proton to make carbonate. All of these are going on all the time, which is one of the reasons why if you take tap water, if you take like distilled water and leave it out, and then you measure the pH, you don't measure 7. You measure something that's acidic because of the carbonate that has been starting to dissolve into into the water. Now, one of the things carbonates will do is that there's an equilibrium with calcium. And calcium carbonate here is a white solid. Now, tap water has a little bit of calcium in it. It's one of the things that makes hard water, quote unquote, hard. Have you ever left out a glass of water for, 2 or 3 days and come back and notice that it's cloudy? Well, that's what's going on. The water that comes out of the tap has not been exposed to the air because it's been in contained pipes. But now that you have it in your water glass and it's sitting on your end table in your bedroom or something, it's equilibrating. Carbon dioxide is dissolving in, and it's becoming acidic, and you're generating some carbonate. And that carbonate then couples with the calcium that is naturally present in drinking water, and it forms a cloudy suspension of calcium carbonate that you can then visually see. So knowing what the equilibrium constants are for various ionic compounds helps you determine when things like that are going to be happening. And so they have impacts on water purification. They have impacts on fluoride content in water, what it should be in order to help with dental health and such. The textbook, in the section, there are 2 sections. There's one section on solubility products in particular. And there's a second section on coupled equilibria. That, like I said, they don't really introduce any new content, but they are extremely rich in examples that they go through working quantitatively and giving real-world examples of that show how this particular idea of a solubility product or how, in the case of coupled equilibria, how Le Chatelier's principle with multiple equilibria, one changes in one equilibrium can affect how another equilibrium works. And so those two particular sections are extremely good in terms of going through a bunch of those examples so that you get some practice with them. And so I recommend looking at them with some detail. This carbonate a set of equilibria is the other primary equilibrium that is used in the small group activity this week. So we have the phosphate version and the carbonate version, both of which are very important in the buffering action of blood. And that is pretty much, let's see, did I miss anything on the list of topics? The only other thing is one piece of terminology, the common ion effect. Which is simply saying that when you have coupled equilibria, they are coupled by the presence of an ion that is present in both of the equilibria. So in this example here, there's a common ion effect with the hydroniums. There's a coupled ion effect with the bicarbonates. And so, so what this means is that if you have a change here that affects the concentration of the carbonic acid, let's say this one goes up. Le Chatelier says the reaction is going to shift this way, making this go up. Well, if that's going up here, it's also going to go up here, which means that this equilibrium is going to shift that way and the carbonate is going to go up. So that's the general idea of a common ion effect. I personally find that this kind of notation that I just used right here, saying here's the perturbation, what effect will it have on the equilibrium, what effect does that have on other components, and drawing them as arrows, do they go up or do they go down? That helps me trace through the sequence of interconnected effects. Okay, and so that's really it on the content. Does anybody have any questions on any of this? Okay, well, so tomorrow's going to be identical to today. Wednesday and Thursday, I will go through muddiest points and such. I am happy to talk at that point about any of this content or to talk about the small group activity. I've gotten a few people that have come to my office hours already to chat about that, and I think they've found that somewhat helpful. So feel free to drop by my office hours, and we can talk about that too. I will get the official due date of the small group activity changed this afternoon. Thank you very much.